So let me get started. I guess today fewer people will be joining us. I was expecting a few people to join, but anyways, let's start. It's already time. Uh, Welcome all to the live interaction session 5 for the NPTEL course of and applications. Of course instructor is Professor Shisha Rao. I'm the teaching assistant. I'm Shri Sai Gupta. Uh, I hope everyone is able to hear me and this video is getting recorded. I have made sure of that. But anyways, uh, for those of you who have not uh, who are watching this video or started watching this series for the first time, I am Shri Sahai Gupta and I'm Shri Sahai Gupta. Uh, I am a Prime Minister Research Fellow at IISc Bangalore. I'm doing my doctoral degree from here. And I did my bachelor's from IIT Ropar in 2020. Uh, After my bachelor's, I briefly uh, joined industry, and specifically Hindustan Petroleum. Uh, this and I'm currently finishing my fourth year of my PhD. Here are my contact details. You can visit my website and LinkedIn if you would like to. And let's get started. Let me do a small recap of what we had done in the last few classes. Let me first quickly review what we have been doing overall. So the first lecture was about uh, an overview. Let me not do that here, and let me just type things out. So what we did in the first lecture was an overview and specifically features of flows that come under uh, come under the umbrella of Gasdynamics. Then we had lecture two, and lecture two was a continuation where I picked up the point, 2 points actually. First point was that energy and momentum equation equation gets coupled, and two, why high speed flows in quite interesting. We'll have a look at that. Uh, okay, this was lecture two. Now, by this time, by this time, 2 weeks were over. 2 weeks of video lectures were over, and uh, a third video. Actually, when I started the third lecture, the topic was the corresponding week's topic was integral equation, and I thought it would be a good idea to emphasize how the conservation equations in its two fundamental forms, uh, integral form or partial differential form, integral form or differential form, have two different, like it's a uh, it's a double-edged sword. One edge is helpful in certain scenarios, while the other edge is helpful in another scenarios. More or less, when you need averaged quantities, when you need overall effects of a flow around some boundary, then probably you would go for high this integral equations, as integral equations do this overall integration or overall summing up uh, over this boundary inherently. But when you need local details and distributions, you go for PDEs or partial differential equations. And that day, by example of jet propulsion in aeroplanes or gas turbines, we saw how integral equations are applied. So part of the solution was basically integrating over the pressure forces. We assume that there are no viscous forces, there are no drag forces on a thrust generating body. Thrust generating body is the gas turbine of the airplane, and generally speaking, the drag over this body will be much lesser than the wings of the aeroplane, and therefore you don't need to really consider this. Uh, just give me a second. Just give me a second. Let me just see. So I don't know if let's see if no. Anyways, okay, no wait. Yeah. So I was saying, yeah. So this uh, this aeroplane, uh, this when you calculate thrust, part of it is pressure calculation, and the other part is the integral of pressure forces of the fluid flowing through it, and that we could again calculate by just measuring the velocity and the pressure at the inlet and the exit of the turbine. We don't actually need to integrate it over the boundaries or the walls of this gas turbine. Okay, so that is something that we saw. So uh, we roughly witnessed their power. In fact, toward the end, I promised discussing two things. One was in wind tunnels, you actually can calculate drag forces by just measuring the velocity deficit behind the wind tunnels. Uh, and secondly, there will be some velocity deficit for sure, and that velocity deficit allows you to calculate how much flow has been displaced because of this body or this aerofoil, and using that you calculate the drag on this aerofoil, because the amount you have displaced had some momentum, and if you take a large enough control volume, you will realize the amount of momentum leaving this control volume must be applied as a force on this aerofoil. And similarly, there was also some discussion on lift calculation by measuring velocities at the forces at the top and the bottom walls of the wind tunnel. So something on that sort. I did not fully discuss it because of time was short, and also again it was simply an extending exercise to be just extended. So and also these things are given in the books and so on. So just went ahead with it. Then came the lecture 4, and lecture 4 was about this is the last lecture we did, and this was about normal shocks. And the first problem we did with normal shocks was uh, pitot tube. So the problem we did was pitot tube, and this problem was given for multiple reasons. Two multiple reasons were uh, the first reason was that we wanted to identify dynamic pressure in high speed flows. Two, how in the limit of what happens to stagnation pressure in the incompressible limit. And two, then there were discussions on standing shocks in front of pitot tube, tube in sonic, supersonic flows. And finally, there was also a discussion on ensuring that if and then calculating the Mach numbers based on static pressure before the shock and stagnation pressure measurement behind the shock. We briefly then discussed one of the doubts from one of the student, which was how does a normal shock appear? I don't exactly remember what his doubt was, but it was kind of how physically a shock appears and why what causes the shock to appear if there are subsonic conditions prevailing near some boundary. Why does a shock appear? That was the rough question. And towards the end, I started discussing entropy of entropy change across a normal shock. So today we are going to focus on this last part. So let's go ahead. Uh, Fine. So for the benefit of people who have not looked at, wait, I need to move to the next slide. So let's move to the next slide. For the sake of the people, let's start with the governing equations for the normal shocks, and we'll pick it up from there. Okay, so this is the first equation that we use. Then comes the momentum equation. This I remember by experience, or you can call like I remember this. I have learned this or something of that sort. It's just to for you to know. You can just go and check the books. These are the three equations that for a normal shock. One is the flow conditions before the shock, uh, and two are the conditions behind the shock. One more important thing is this is a standing shock, so shock is assumed to be stationary and it does not move. And it's only the flow behind and ahead of it which is moving. The flow ahead of the shock will be supersonic, behind it will be subsonic. That's the idea. Um, what else? Okay, there are a couple of things to be noticed, which is that the flow, this normal shock is a adiabatic process across from 1 to 2. The total enthalpy is not going to change, and so because the total enthalpy is not going to change, the sonic enthalpy is also not going to change, sonic speed is also not going to change, total temperature is also not going to change. So any quantity which depends on sonic temperature or uh, total temperature is not going to change. So that is something that we need to note. Now, the easiest way or the memorable way of deriving the Mach number behind the flow, behind the shock, is to use this property of constant total temperature or sonic temperature. So we'll use it. So before doing that, let's first define what is the sonic. It's not the sonic velocity. I should maybe correct myself to say star sonic speed. So star sonic speed will follow this logic that h. Um, we are basically saying that rather than taking it to isentropically to stagnant conditions, we are taking it to isentropically to sonic conditions. That is our aim, and that when we do that, we are going to reach sonic these star conditions. So that is what the star conditions are. So let me just write that down for you. A star will be gamma RT. So gamma RT star. Now what will be the T star be? So that is something that we need to check. So in during these star conditions, H can be written as CP T star. Again, noting that all this that we are able to write, we are able to make assuming by considering the case of a calorically or thermally perfect gas where the specific heats are constant and does not depend on anything, they're just constant. Now this is gamma RT star uh, Mach square. So Mach here, because we are assuming sonic speeds, so gamma RT by 2. This is also, this thing is fine. And then you have CPT plus again gamma RT by 2. And then you have Mach square. So Mach square, let me just see if I've written it fine or not. This is all okay. CP I want to write as gamma upon gamma minus 1 R. So that I want to write, so I'll just write that. Okay, so once this is there, uh, what essentially we have is I'll write T star by T or T. Well, yes. So now we have, see, you can cancel gamma from everywhere. In fact, let's divide gamma, this CP thing itself, so that you have this gamma minus 1 everywhere. R will get cancelled. So let me do this also. This will become plus 1 T star. This will become 1 plus gamma minus 1 Mach square T. This is how it will look. So you can just check for yourself. And so this once you do this, if you write this here, you are going to get 2 divided by gamma plus 1, and here also you are going to get. So I could have just simply borrowed the values for the other formulas, but let's just go ahead and derive it once more so that it becomes clear to you what is the easiest or what is the most intuitive way. We can just go ahead and start randomly splitting things. I don't like that method because well, it does. There is no clear path how to go about the derivation. So that is one reason. Anyways, let me just check if I'm typing it correctly or not. The temperature formula, I'm pretty sure it's fine. Let me just see once. Okay. I'm not able to uh, like uh, get the exact formula, but I think this one is fine. Mm, should we actually do this one is okay, I guess. I'm not sure, but anyways, now you just have to do one thing. Uh, See gamma RT, this becomes A star, and so now if you multiply both sides by uh, this is A star square. Let me just correct that too. So if I do that, I will get this will be A star. This will be A, which I can write as A can be written as U gives U a U square by Mach square, right? So divide by Mach square. Something is wrong. Wait, I made a mistake somewhere. Let me check. Hi, can I know your name if you would like to introduce yourself or no? Madam, I guess not. He is not fine with doing this. Anyways, let's go back. Uh, so we were here. A star square is gamma RT. Then we started writing the sonic speed. Wait, there is an issue, I guess. What's the issue? Issue is so we were substituting for the like we substituted this temperature in the energy equation, and we got what did we get? Let's just do this again. Let's try to do this again. Uh, so basically, we will have T naught is the stagnation temperature will be T upon 1 plus this is the stagnation temperature. Now, if you want to write the stagnation temperature in terms of uh, uh, sonic temperature or start temperature, basically it comes around 2 by 2, yes. So it's basically, so this one is fine. So this much formula is okay. No issues. Now we substitute this here. We get T star, gamma R, T star is A star. This you get is A square. A square can be written as Mach square Let me just. There is one more error which I made. That is what? No, this is the error. Actually, this should be upstairs. Okay. Now once this is there, a square can be written as u square. So a is what? A is u by m is u by a. So a is u by m. So you will get mark square here. Now once you divide it on the if you take it on the other side, you just simply have this. And this itself is inverse of mark star square. So you have 1 by mark star square. Right. So now there is another important thing, or let me think if we can relate. Yeah. So rather than writing it as mark star square, let us just simply write it as a star square into u square. This is all right, right? Now I am saying that because across the normal chalk, you have this. Oh, he is gone. Anyways, across the so we know what do we know that is. So we'll use this. Wait. So this one we know that a star one. Let me write that down. So we have so we have a star, and this should also be square. I'm making some small typos. Okay. Now so a star one indeed equal to a star two. So what we can use here is this can be written for m1. This will be equal to what? So now similarly we can write it for m2 also. Now once you have written for m2, you know this is u2. So now you know what is u1 by u2. So let's write that down. Yeah. Let me think. There is one more relation that we need to go ahead with the derivation. So just give me a second. Let me check. We need to start substituting things. That is that we actually require that. So the idea here is okay. Uh, Wait, let me think. So if I just differentiate this thing, or sorry, divide the two equations, uh, what do we have here? Okay. Now, maybe we can't use it as such in this form. Okay, fine. Let's do this more. So this derivation will, so you have P1 plus, so rho 1 U1 is a constant, so you can just write as, let's say G, let's say this is G. So you have a constant here, G by, I think G by, what is it? G by rho 1, right? Equals to P2 plus G by rho 2. So wait, this is rho, no, no, so G1 U1. So G into U1 and G into U2. Or maybe that's, I'm getting stuck with the formula, this derivation. And let's not waste more time. Let's just go ahead with the derivation. Not the important part. Wait. Yeah. So I thought, wait, where is the cursor? Yes. So, anyways, uh, there has to be some more steps which I am not like recalling right now. Thought there is a very straightforward way to go ahead with it, but obviously no. Uh, Anyways, there are a couple of formulas that let's just simply use them right now. Okay, so the first formula is, let me just write that formula. Okay, oh, okay, right. Let me just write this formula. Then we have 1 plus. So this is the formula that we need to derive. Uh, then we have another formula. Which is rho 2 divided by rho 1 is equals to U1 divided by U2 is gamma plus 1 and 1 square divided by 2 plus minus 1 and 1. Okay, so this is one important formula that we are going to use. Then another important thing is what is P1 by P2 or P2 by P1. Okay, so P2 by P1 this sort, it will be 1 plus 2 gamma plus 1 and 1 square minus 1. Okay, so now we are almost done. We don't need any more formulas now. So now let's look at yeah. So now that we okay. So now that we have these two important things, let's just go ahead. What are we doing? Let me just point that out too. We are now going to look how entropy across a normal shock increases, or how much does it increase. Okay, and then we are going to combine. We're going to see some cool properties around that. So across a normal shock, we know that there is a entropy change, but because we have a calorically perfect gas, we can write the TDS relation to find the entropy change. See, TDS relation can be written as CP minus VdP. CP again becomes oh, gamma R by gamma minus 1. Then you take this down to write as this thing. This becomes RT by P, and that T gets cancelled, so it's the R by dP by it's of this thing. Now, see, entropy has a unit. What is the entropy's units? Entropy's units are is from joules per kg and Kelvin, right? Heat per temperature, right? And what is the units of CP, or let's say CV? It's also joules per kg Kelvin. So now in order to basically we are going to see the qualitative or normalized change in entropy. We are going to see how much entropy is going to increase or decrease. But to quantitatively identify what is high and what is low, how much, when we say how much, we want a degree of highness or lowness. To estimate that, we are going to normalize, non-dimensionalize entropy, and so that we are going to do with CV. So this when we integrate this equation, or rather, let's not integrate it just right away. This I write CV is R by gamma minus 1. So you will have gamma dt by t, and you will have minus R, sorry, gamma minus 1 R dP by P. Okay. An important thing here is that we should just simply substitute dt as equals to what. So uh, at this point we can just, because we have the formulas for density and pressure ratios, we don't have a formula for temperature ratio. We can derive it, but we can also substitute the temperature relation. So we have basically, so what do we have? We have dp equals to t d rho plus uh, so we have dp by p is d rho by rho plus dt by t, and from there we can substitute that it will be dp by p minus gamma d rho by rho. Does that make sense? Now this gamma, and don't know if it got highlighted or not. See, we are here. So now this gamma, oh, you can't see that. So now this gamma and this gamma can cancel out to give you what? Plus. There will be also no R. So I need to note that down. I have to remove this R also from here. So you have this relation to follow. Now let's just integrate this to get, and note that this is some sort of non-dimensional entropy change. This is equals to ln P2 by P1 minus gamma ln rho 2 by rho 1. So this is the relation that we're going to use. Now let's substitute this thing. Okay, now let's discuss the plan of what is this? What is this are we doing? See, there are a couple of things. The first thing is that why don't we see any shock at subsonic flows? Okay, and we are going to show with the help of uh, the case of calorically thermally perfect gas, calorically or thermally perfect gas, that in subsonic flows, any shock wave will be decreasing the entropy. And so that is not possible, and that is why we don't see any shock waves at subsonic flows, uh, or at least in the sustained cases when thermodynamic equilibrium occurs, we don't see any shock waves, persistent shock waves. Then, then next, what we are going to see is that in the limit of weak shock, weak shocks, why does Mach waves or normal shocks themselves can be treated as an isentropic process. So we'll see that also. So that is something that is the plan. So just follow along the derivation. That's it. Okay. So now, uh, and the thing is that we are going to take the limit of M1 tending to 1. That is the limit of weak shocks. Okay. And only in that limit we are going to see some simple formulation coming up, and then we will be able to make some good uh, comments. Otherwise, the problem the formula is too like it's too convoluted. So any straightforward comments are not possible. Only in that limit that that formula goes to some simple form, and then we can make some change, make some arguments based on that. So what are we going to do? We are going to consider the limit m1 tends to 1. Okay. So with that, let's go ahead and substitute limit. So this will be ln 1 plus minus gamma ln. And you have this term. Okay, so now our plan is that in the limit m1 tends to 1, we have to bring this term out, this m1 square minus 1. That is the term that is going to 0. So we have to use that uh, this term has to be used. Okay, so the formula is going to be expanded in terms of this variable, and so we need to find out this form even in this ratio. So let's do that. So if we do that, what exactly is this? This is m1 square minus 1 plus gamma plus 1. Okay, and this one will become minus 1 uh, plus gamma minus 1. Now, why am I doing this? I'll tell you. First of all, see that this gamma minus 1 plus 2 becomes gamma plus 1, so that we can remove this plus 2 from here. Then the next thing we are going to do is break this ln into two ln's to give you two things. Let's do that. And now, because there are minus and minus, so you're going to get, yeah. And then this is the thing there. Let me think one more. We can do one more thing. Why not divide gamma plus 1 on the both sides so that we can get some good things out there, right? Right. So this can be written as 1 plus m1 square. This is also 1 plus of this sort. So now you have 1 plus m1 square, and then you have this there. Okay, so let's use this on the next page. Okay, what we are going to do, the expansion that we are going to do is of this manner. So let's see, limit x tends to 0, ln 1 plus x is x plus, so x minus x square divided by 2 plus x cube divided by 3 minus, and so on. Okay, so with that, you're going to get some interesting things. But because I don't want to write lot of times, let us write that there is this c, or yeah, there's this c which is, or this variable a. Let me define this variable as some variable p or q r s t u v w. Let's just define it as a. Please excuse me for a second. Okay. So I was saying, let us denote this a as this m1 square as a, and b as b as what? B as b as nothing else. So now what we have here is, or let us just define it as epsilon. Okay, epsilon is a value which will go to 0. Okay, okay. Now let's see what do we have. Uh, we will have we will have 2 gamma minus gamma square plus epsilon square plus this entire thing. We'll have epsilon cube. This will be also cube. This will be cube. This will be 8, and so on. I'm not writing the fourth other term for some specific reason. We don't need to take care of that. Essentially, that is the reason. Now you have, now we are going to calculate this one apart. So you have minus gamma. So we have gamma, that is epsilon, and we also have Or no, let me just write this thing down first. Okay. And then we also have finally plus, what do we have? We have this term. Okay, there is this minus sign I didn't take care of, so that I need to take care of. So this becomes minus. And I also have to multiply this gamma here. Uh, this thing is squared. Okay, this thing is squared. This is gamma square. This is plus 1 minus 2 gamma. Okay, and then we finally have one more thing. Plus, this is cube. Okay, this will be gamma cube minus 1 minus 3 gamma. Well, let us just do this simple way. Okay. So a little bit of manipulation is needed at this point of time. So let us just do that. Okay. Okay. And so on. There is also something called as so on. This is gonna be good. This is gonna be there. Now let's see the individual terms. So what terms do we have on this side? We have what? We have 2 gamma. Then we have minus gamma, gamma plus 1. Then we have minus 1. This is the numerator of the first order term in epsilon. Okay, you can see this 2 gamma is coming from here. Then because there is no denominator here, so we multiply gamma plus 1 on this one. So we get minus gamma into gamma plus 1 and then gamma into gamma minus 1. What is this? Gamma square minus gamma square. So this second order term gets cancelled. Then this is minus gamma and this is minus gamma plus 2 gamma. So this, you see that the first term gets first order terms, there is no first order term only. Okay, that is the important thing. Then the second important thing is 4 gamma square. Then you have gamma square is gonna be there into gamma plus minus this term. So let's just, this is again the second order term. Okay, so just we'll see if this one also is, there is a cancellation here also. So you have gamma cube minus gamma cube and gamma cube, which gets cancelled. Then you have minus gamma, wait. So gamma cube and minus gamma cube gets cancelled. Oh, there is a mistake that I made. This has to be by 2. This also has to be by 2. So you will get 2 here. Here you will have 3. Here you will have 3. See, there is this mistake that we keep on doing. This will be 2. This is going to be 3. This is going to be 2. This is going to be 3. Okay, this is going to be 2. And this is going to be 3. I guess this one is fine. So once this is there, this will be minus 2. And now you need to actually multiply 2 on both sides. So this becomes 4. Think this will be gamma square. This is okay. Just let me think. Okay. Oh, this will not be gamma square, man. Come on. This will be just gamma. See, mistakes I have done. A lot of mistakes which I have done is this will also be gamma. Okay. Now, so here also it will be gamma. Okay. Which is what? So, yeah. So this is what? This is gamma plus minus 1 square, right? So, and now you see if you take care of this term, what you're going to get is gamma plus 1 square minus gamma minus 1 square is 4 gamma square, 4 gamma, and then you have outside minus 4 gamma square. So you see the first, see these two terms will get cancelled. These terms will get cancelled if they are all combined. Okay, so the first two terms get cancelled. So it turns out that the first order and the second order terms are getting cancelled out when we see in that limit, and only the third order terms are going to remain. So let's calculate that third order term and then we'll make some commentary on the what is going. Okay. 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 So now let's write what do we have here. The third term, the denominator is gonna be this thing. Okay. So this is the denominator, and we also have this epsilon cube here. Okay. So now we have 8 gamma cube, then we will have gamma and gamma plus 1 ka cube. Okay, then we have uh, I think gamma minus 1 ka cube. E- What? Plus gamma minus 1 ka cube. Okay, so now what is that? The gamma plus 1 ka cube is gamma cube plus 1 plus 3 gamma square plus 3 gamma, right? Gamma minus 1 cube is gamma cube minus 1 minus what? So it's what I don't know. So gamma cube is minus 2 gamma. Uh, wait. So minus 2 gamma square and so minus 3 gamma square and plus 3 gamma. Yes. So you have minus 3 gamma square plus 3 gamma. So what is going to happen is gamma cube 3 gamma is gonna get cancelled, and what is gonna remain is uh, 8 gamma cube, and what is gonna remain is this will be so this will be 3 gamma square so plus is minus this is minus 6 gamma square just minus 6 gamma square minus 2. Okay, so which is gonna come to equal to 2 gamma cube minus 2 gamma. I think plus 2 gamma. So now you can take 2 gamma common, and you're going to get gamma square plus 1 in the the common factor. Now this is limit delta s in this scenario. Okay, what is gamma when this? What is this? This is m1 square. This is the thing there. Uh, One more thing is the expression for delta p. Okay, we have certain expressions. Let's move ahead. So now this is the expression we have got. Now what will be the delta p by p1? Just minus this thing. So you see that this is So actually, need to see this is 2 gamma here. Okay. So now you can see what we have here is you won't need this term there. We have 3, but there's a problem. The problem is 1 2 gamma is fine. You need 4 gamma. So this is 12 gammas. I guess this is fine. Let me just check. So this is the expression you will get. Let me just check if we have gotten the correct expression. Yes. So this expression actually we made some small error. Let me just see. Actually, this is what it is gonna come. So correct that. It's gonna come like this. This is the expression you're going to get. 2 gamma, 2 gamma is 1, m square minus 1 cube by 3 plus gamma plus 1 square. Okay, this is what you're going to get. Now, if you substitute this thing there, you're going to get 12 gamma square is fine. This will be gamma square minus 1. Or gamma minus 1. Yep. So this is fine. Now let's draw the commentary that I wanted to start with. Okay. From this expression, the first thing which we note is that if m1 is less than 1, delta S across a compression wave or a compression shock will be negative. And it was the towards the end of our discussion in the previous session where I mentioned that in a adiabatic flow where there is no mass transfer also that is not happening, uh, entropy cannot decrease because there is no heat rejection and there is no mass removal also. So delta S is generally negative. Okay. Now, uh, so that is why below in subsonic flows you can't see a shock wave. First of all, from this expression, the second expression is showing that the you note that this is delta P star. Delta S is proportional to delta P star cube. Delta P star can be thought of as a strength of the shock wave. We see that the entropy increase in a shock wave is thrice or of third order of what the shock strength is. Now, in a shock strength, in a shock normal shock, you see that if delta P is of this sort, if this is delta P star, then y, this is y-axis, and you see this is delta, this is y equals to delta P star. But what you will note is that this will be delta S star. For weak shocks, delta S is very low. Suppose delta P star is very low. Then we know that delta S star is much smaller number. delta S star is a much smaller number. And that is why in the limit of weak shocks, we can consider that the entropy is a constant. So it is not a constant, strictly speaking. It will be a very small number, but it will be a like it will be a very small number. It will not be a large number, but it will be some value. It is not like zero, exact zero. It's not exact zero. And however, thermodynamically speaking, we don't care for that small entropy increase, although there is some entropy generation, but that is insignificant entropy generation. So even a weak shock is not isentropic exactly, but for all engineering purposes, for all kind of purposes, we don't need a very the entropy generation will not be very large. And so in the limit v of the weak shocks, we can see that the entropy increase is this uh, is of third order. Also, away from this limit. See, in the limit m1 tends to 1, delta p tends to 0. Only in that limit, this formula is valid. Otherwise, it breaks. So otherwise, this is not even right. This part of it is not even correct because it does not exist in that limit. It only exists in this limit. And I just wanted to show that in this limit, it's thrice. If the delta p is small, delta s will be thrice, like it will be to the third power, it will be that smaller. If it's zero point 0.1, if this is delta is zero point 0.1, delta s star will be 0.001. So you see how quickly it goes to zero in the limit of weak shock. So that was the intent with this problem. So now let's do the next problem, and this problem uh, is for the moving shocks. Okay, so let me tell you what the problem is. Okay, so the question is uh, anyways, an shock moves in a constant area tube in a region where velocity is t meters per second, temperature is 298 Kelvin, and pressure is this 1 atmosphere. The shock speed with respect to lab for a true lab coordinate system is 500 meters per second. Find a low velocity behind the shock and B Mach number corresponding. Okay, so we'll do this problem and we'll try to uh, stop today. Let's do this small problem. Now, let me just draw the shock. See you now with this today's week lecture. you would note that you won't see a static shock very often. It's generally a moving shock, right? But it's up to us, our coordinate system, that we can make the shock stand. And as we have been familiar, more familiar with the static shock, I would like to do that, solve the problem in that domain. Okay, so nothing fancy there. It's a simple problem. Let's just do this. So otherwise, the shock is moving with a velocity of 500 meters per second, and the the velocity of the region, or the region is just 50 meters per second. So we need to calculate what is going on behind the shock, and this is in the moving frame. Okay, so let's just go into the standing frame. Okay, in that frame, we see that the upstream flow, or the flow ahead of the shock, will come at 450 meters per second. The static conditions are not gonna differ with the changes of our coordinate system. So we can say that P1 is 1 atmosphere, T1 is 298 kelvins. That does not change, and U1 is 450 meters per second. I will also calculate A1. Okay, A1 is gonna be gamma RT. So let me just calculate that. And we are also told that the gas is air. Let's consider that. Uh, so with that, we have 1.4 times 298 into R 287. Uh, oh, 1.4 into 98 into 87 is 346 meters per second. So in this reference frame, what is the Mach number? So we have 450 divided by 346. Its Mach number is 1.3. Okay, so now I'll use the formula that we had written down some time before of M2 related with M1. This one we can use because this is the relation for the static shock wave. So if I substitute this value in here, what am I going to get? This gamma minus 1 is what? 0.4. So this is 0.2. This is 1.3 square. Square, this is again 1.4, 1.3 square, and this is what? 0.2. Okay, so what is square? So M1, M2 is coming up to be 0.7859. Okay, so let's just write that there. Okay. This is our Mach number. We know stagnation temperature is gonna remain same. So because we need the velocity, we need to calculate the velocity first of all. And once we'll calculate the velocity in this standing shock, like standing shock reference frame, we'll go back and then we will calculate flow velocity and corresponding Mach number. So first we need to find out the velocity in this era. Now yes, we can also calculate T2. So how to calculate T2? We're going to use this formula that T2 plus 1 plus gamma minus 1 by 2 is 0.2 m2 square is equals to T1 0. T1 and plus 0.2 m1 square. So if I do that, first of all, so let's calculate what T2 is. So we have 1 plus 0.2 into m2 square is what? 0.786. So point square divided by 1 plus 0.2 into 0.786 square. What is T1? T1 is 298. So we calculate T2 to be T2 comes out to be 354.9 Kelvin. What is our A2? Let's just calculate A2. A2 will be just gamma times 287 to the 4.5. A2 is 377.6 Kelvin. What is our U2? U2 will be this times 0.786. This is 296.88. Now this U2 will be subtracted with 500, which is what? Which is 203.2 meter per second. Okay, so this is the answer 1 to the problem. Answer 2 again, static quantities can be extended back. Static quantities you don't need to calculate. Stagnation quantities change. Static quantities do not. So now M2 will actually be in this domain, in this reference frame, M2 will be how much? Let's just calculate. It will be around 0.5, little higher than 0.5, 377.6. 0.538. That's your answer. That's the simple answer. So we're going to stop here today. This is the discussion I wanted to have. There are a couple of questions I also wanted to do more, but I will stop today because I'm feeling a little headed again, heavy-headed, not feeling very well. We're going to continue whatever is left of this. There is one more question I wanted to do on this in the next lecture. Okay, so I'll see you next time. Yeah.